if you're here, it probably means you're ready to slow down, relax, and drift gently into the night with a head full of curiosity. Tonight, we're going to unravel one of the most quietly bizarre topics in all of science, the strange states of matter. From solids that aren't really solid, to crystals that tick with the rhythm of time itself, we'll take a soft and soothing journey through the hidden lives of molecules. Now, I do hope this video doesn't end up being too interesting. That would be terribly inconvenient for your plans to fall asleep. But if you do find yourself still awake by the end, at least you'll be armed with the delightful knowledge that some solids flow, some fluids behave like crystals, and some things don't seem to make sense at all, but do anyway. It's the kind of bedtime story only physics could write. Before we begin, if you're enjoying this gentle stroll through science, I'd be ever so grateful if you gave the video a like and subscribed. It really helps this cozy little channel float along. And if you're feeling friendly, let me know in the comments where in the world you're listening from and what time it is where you are. I love imagining our little global campfire of sleepy minds, stretching from starry towns to midnight cities, all connected by curiosity. This video is here to relax you, to fascinate you just enough to make your thoughts soft and meandering. You won't need to remember anything. Just float with me as we explore matter that moves, shifts, vibrates, and defies definition. It may sound like magic, but it's all real. And just before we begin, this video is for relaxation and education. It is not medical advice or a substitute for professional care. Always look after yourself and sleep well. What is a solid? It sounds like a question with an obvious answer. A solid is something that holds its shape, that doesn't flow or squish unless you really try. A rock, a chair, a spoon. Solid, right? But hold that thought gently, because as it turns out, even something as basic as the idea of solid is much more slippery than it seems. The classical model of matter tells us there are three states: solid, liquid, and gas. Maybe you learned it in school with a tidy little diagram. Solids are rigid, liquids flow, and gases spread out. But that's just the beginning of the story, and, depending on who you ask, maybe even a bit misleading. Let's start with the basics. In the classical view, solids have a fixed shape and volume. The atoms or molecules are arranged in a repeating pattern, usually locked into a neat crystal lattice. They can vibrate in place but don't shift positions. Liquids, on the other hand, have a fixed volume but no fixed shape. Their particles are close together but can move around each other, giving them that signature flow. And gases, their particles are much farther apart and move freely, filling whatever space they find themselves in. This neat trio was a helpful way to understand everyday materials. Ice is solid, water is liquid, steam is gas. Three forms, one substance. Explained with elegant simplicity. It works just fine if you're cooking dinner or teaching a classroom of 12-year-olds. But the universe has never been particularly interested in simplicity. Let's take a closer look at solids. Even within what we casually call solids, things start to unravel. Not all solids have neat, orderly lattices. Some materials, like glass and obsidian, are disordered at the atomic level. Their molecules are arranged more like a liquid that's been frozen in time, jumbled, irregular, and not quite locked into place. They're called amorphous solids, and they don't behave the way we expect traditional solids to. They might look solid, feel solid, and even clink like a solid, but on a molecular level, they're more like slow-motion liquids. It turns out that solid is more of a behaviour than a strict category, and that's a recurring theme in the world of matter. The boundaries are often fuzzier than they appear. Take pitch, for example, a sticky tar-like substance. At room temperature it seems completely solid. You can tap it with your knuckle, but left alone for long enough it flows. In fact, there's a famous experiment that began in the 1930s at the University of Queensland. A blob of pitch was placed in a funnel, and researchers have been patiently waiting ever since. It takes around 8 to 13 years for a single drop to fall. That's a flow rate that makes molasses look like a sprinter. Still, it flows. So, solid or liquid? Meanwhile, liquids and gases can blend into each other too. There's no sharp dividing line between the two. At high temperatures and pressures, substances can reach a supercritical state, a phase that has properties of both. It can flow like a gas but dissolve substances like a liquid. In this twilight zone, even our tidy chart starts to look more like a mood board than a map. But wait, there's more. If you cool things down enough, or heat them to absurd temperatures, you can discover entirely new phases. These aren't exotic exceptions. They're very real, and in some cases quite common. Plasmas, for example, are found in lightning, in the sun, and in fluorescent lights. They're often called the fourth state of matter, but in truth there are dozens of known phases depending on how you define them. Some materials change structure under pressure, others reveal hidden states when exposed to magnetic fields or electric currents. Why do we even try to label these things then? Well, for the same reason we name clouds or group animals into species. It's how we make sense of a world that refuses to sit still. Phases of matter are defined by how molecules interact with each other and how much energy they have. Temperature and pressure are the big players here. Add heat, remove it, compress something, and you can often change its phase. But in quantum systems, or at extreme conditions, the rules start bending. Sometimes they do backflips. One helpful way to think about matter is not in terms of rigid categories, but in terms of phase transitions, those magical in-between moments when everything is shifting, melting, freezing, boiling, condensing. These transitions are where the real drama happens. Molecules begin jostling in new ways, structures rearrange themselves, and properties change dramatically. What was once brittle becomes slippery. What was fluid becomes structured. Even our breath demonstrates this in miniature. On a cold morning, you can see your exhalation condense into mist. Invisible water vapor turns into tiny liquid droplets in the air, floating briefly before vanishing again. That little puff is a transition caught in motion, a delicate reminder that matter is always ready to change form, given the right nudge. Our classical three states of matter are like the surface of the ocean, visible, familiar, and somewhat predictable. But beneath that surface lies a vast, shifting landscape of molecular behavior. Sometimes it's orderly, sometimes chaotic. Sometimes it defies our expectations entirely. That's the thing about nature. It's under no obligation to be simple, only to be consistent. And even that consistency is written in a language we're still learning to read. So while it's comforting to think of solids as firm and dependable, that comfort is more psychological than physical. In the world of atoms and molecules, solidity is often a matter of patience. Wait long enough or change the conditions just so, and the truth will start to melt around the edges. Matter, it turns out, is a lot like us. It has phases, it flows, it holds together until something makes it shift. And sometimes it exists in a state that doesn't even have a proper name yet, just waiting for someone curious enough to notice. If you've ever looked through an old church window, or wandered past a centuries-old building with wavy, slightly distorted glass, you might have heard a curious explanation. People often say that the glass has flowed over time, thickening at the bottom because it's not a true solid. It sounds like a scientific whisper passed down through the years. Glass, they say, is just a very slow liquid. It's a compelling idea, full of mystery and quiet motion. But as much as we love the poetry of that notion, it's not quite true, or at least not in the way it's usually told. Let's start with the basics. Glass is what scientists call an amorphous solid. Unlike crystalline solids, such as salt or diamond, glass does not have a regular repeating atomic structure. If you could zoom in close enough to see the atoms in a chunk of quartz, you'd find a beautifully orderly grid. Every atom would know its place. In glass, on the other hand, the atoms are arranged more like a frozen liquid, disordered, irregular, a sort of arrested chaos. They're stuck, but they're not lined up like neat soldiers. It's more like a crowded room where everyone stopped moving mid-conversation. This lack of structure is what gives glass some of its unusual properties. It's hard and rigid, like a solid, but it lacks the long-range order of a crystal. Technically speaking, the molecules in glass don't sit still. They vibrate in place, just like in other solids, but they never quite settle into a repetitive pattern. It's a bit like a party that never fully ended. Things quieted down, but no one ever went home. Now, about those old windows, the myth that they're thicker at the bottom because the glass has flowed over time is a stubborn one. In truth, the uneven thickness is a result of how glass was manufactured centuries ago. Back then, techniques like crown glass and cylinder glass were imprecise. Glass blowers would spin molten glass into a disc, or form long cylinders and flatten them. The resulting sheets were uneven by nature. When glaziers installed them, they often placed the thicker end at the bottom for stability, not because the glass was melting, but because that was just good sense. Modern measurements confirm this. If you examine antique windows carefully, you'll find that the direction of thickening varies. Sometimes it's at the top or the sides. If glass were truly flowing downward over the centuries, that wouldn't happen. Also, the rate at which glass would need to flow to show visible change in a human lifetime, or even a millennium, is staggeringly slow. To observe a measurable shift, you would likely need to wait longer than the age of the universe. Not ideal for an experiment. But here's the fun part. The myth isn't entirely without merit. While glass doesn't flow in any practical sense at room temperature, it does behave like a very, very high viscosity liquid when it's being formed. That's why you can shape it when it's hot. It behaves like thick honey at thousands of degrees. And even after it cools and seems rigid, glass never quite becomes a crystal. It's more like a material caught in the act of solidifying, forever in a state of molecular hesitation. Scientists describe this state using a term called the glass transition. Unlike melting or freezing, where there's a clear temperature threshold and a dramatic change in structure, the transition into a glassy state is more of a gradual slowdown. As the material cools, its molecules move less and less until they appear frozen. But there's no snap, no clear dividing line. It's like watching a crowd slowly fall asleep without any single moment where it becomes quiet. Pitch is another fascinating example. It looks solid, it shatters if struck and it doesn't seem to move, but over long periods it does. In the famous pitch drop experiment, which began in the year 1927, researchers placed a blob of pitch in a funnel and waited, and waited, and waited. It takes years for a single drop to form and fall. Despite appearances, pitch is technically flowing, just extremely, unbelievably slowly. This quality, flowing under immense timescales, isn't exclusive to pitch or glass. Other materials like certain plastics and even metals under the right conditions can exhibit similar behaviour. They don't fit neatly into our traditional definitions. They blur the line between fluid and solid, reminding us that states of matter are often more about timescale than absolutes. Obsidian, a naturally occurring volcanic glass, is another member of this amorphous club. Formed when lava cools rapidly, obsidian lacks the time to organise into crystals. The result is a beautiful glossy black rock with a conchoidal fracture pattern. It's solid to the touch and sharp enough to make surgical blades, but its internal structure is as disordered as any other glass. Nature, it seems, doesn't mind skipping the crystal step when she's in a hurry. What makes all of this even more fascinating is how these materials challenge our instincts. We rely on touch and sight to decide whether something is solid. If it clinks when tapped, or shatters when dropped, we call it solid. But on the atomic level, that impression can be misleading. Molecules don't care how something feels in your hand. They obey rules of motion, energy, and arrangement. And when those rules fall somewhere between solid and liquid, we get materials that are neither, and both. There's a quiet elegance to amorphous solids. They embody stillness that isn't entirely still, structure that never quite finished forming. They defy our categories not with noise or flash, but with subtle complexity. A window pane, a shard of obsidian, or a slow drip of pitch, all reminders that the universe doesn't always rush to decide. Sometimes it pauses in between. And while it might be tempting to think of glass as just a stubborn liquid pretending to be solid, it's more accurate and more beautiful to see it as something unique, not a failure of solidity, but a different kind of order, one that accepts disorder as part of its nature. In a world that often demands neat definitions and hard boundaries, glass offers a different lesson. It reminds us that matter, like time, can sometimes slip between the lines. If you asked most people to list the states of matter, you'd probably get the classic trio: solid, liquid, and gas. Maybe someone would pause and throw in a thoughtful, "Wait, what about plasma?" And that person would be absolutely right. Plasma is often forgotten, quietly left off the list like the cousin who moved out of town and only shows up for solar flares. But here's the surprising truth. Plasma isn't rare at all. In fact, it's the most common state of matter in the visible universe. Not here on Earth perhaps, but step out into the cosmos, and it's everywhere. The stars, the sun, distant nebulas, and even the auroras that dance over polar skies. These are all lit by plasma. Plasma is, in the simplest terms, an ionized gas. That means the atoms in the gas have been energized so much that their electrons have broken free. Instead of being neatly paired in atoms, the particles become a buzzing sea of positive ions and free electrons, zipping around and interacting in electrified chaos. This changes everything. It stops behaving like a gas and starts acting like something entirely different, something responsive to electric and magnetic fields, something that glows, pulses, and can form strange shapes in space. It all begins with energy. Add enough heat or voltage to a gas, and the electrons start to break away. In a standard gas like the air we breathe, the atoms are neutral. They have the same number of positively charged protons and negatively charged electrons. But in plasma, that balance is broken. The result is a material that conducts electricity, generates magnetic fields, and can support waves and filaments that twist and shimmer like cosmic silk. Here on Earth, we don't see much naturally occurring plasma in everyday life, which may be why it slips under the radar. But it is around. Lightning is a brief burst of plasma. The sun's surface, of course, is a seething ball of it. But you don't have to look to the sky to find plasma. Neon signs, fluorescent bulbs, plasma TVs, and even certain types of welding equipment all rely on it. That familiar buzzing light in an old neon sign isn't just a glow. It's ionized gas being excited by electricity, shedding light as its particles dance back and forth. What makes plasma so strange is how it reacts to forces. Unlike gases, which float around rather indifferently, plasma is highly sensitive to electromagnetic fields. It can be bent, shaped, or guided, forming intricate patterns. In laboratories, scientists use magnetic confinement to trap plasma in donut-shaped devices called tokamaks, an effort to harness fusion energy by containing the same kind of plasma found in the sun. It's like trying to hold lightning in a net made of magnetism. Plasma's behavior leads to beautiful phenomena, both natural and human-made. One of the most captivating is the aurora borealis, the northern lights. When charged particles from the solar wind collide with Earth's magnetic field, they are funneled toward the poles. There, they interact with the gases in the upper atmosphere, transferring energy and creating shimmering curtains of plasma high in the sky. The colours you see, green from oxygen, purples and reds from nitrogen, are the result of those atoms getting excited and then calming down, releasing photons as they do. It's a glowing reminder that Earth is wrapped in an invisible shield of magnetic protection, and that plasma is not just distant, it's overhead, painting the night with light. And it doesn't stop there. Plasma is responsible for solar flares and coronal mass ejections, massive eruptions from the sun's surface that can blast particles across the solar system. When those waves reach Earth, They can disrupt satellites, knock out power grids, and light up the skies with especially intense auroras. It's as though the sun occasionally sneezes, and we all brace for the ripple. Beyond our solar system, plasma fills the space between stars and galaxies. The interstellar medium, the glowing arms of spiral galaxies, and even the radiant clouds of ionized gas in nebulae, all made of plasma. It's not just common, it's dominant. If you could tally up every atom in the observable universe and ask what state it's in, the answer would overwhelmingly be plasma. The universe, it seems, has a flair for the electrified. Of course, plasma isn't just a wild glowing spectacle, it has practical uses too. Plasma cutting is used in industry to slice through metals with high precision. Plasma propulsion systems are being developed for future spacecraft, offering efficient alternatives to traditional rocket engines. Even medical sterilization tools and surface treatments use controlled plasma to alter materials at the microscopic level. It's one of those fields where science fiction quietly turns into science fact. Yet despite its versatility, plasma's behavior can still be unpredictable. It doesn't obey the same simple laws that apply to solids, liquids, or gases. It has its own quirks, its own rhythms and instabilities. It can pulse, spiral, kink, and twist. Scientists study its motion with complex models and simulations, trying to understand phenomena like magnetic reconnection, a process where magnetic field lines snap and realign, releasing massive bursts of energy. This is thought to be what powers solar flares and other cosmic fireworks. And then there's the matter of temperature. Plasmas can get astonishingly hot. The surface of the sun reaches about 6,000 degrees Celsius, but the sun's corona, the outermost layer, can reach several million degrees. Why the corona is hotter than the surface is still something of a mystery, but plasma is at the heart of the puzzle. It's a reminder that even familiar things, like our own star, hold secrets waiting to be decoded. Plasma also challenges the neat divisions we like to draw. It shows that adding energy doesn't just make things hotter, it can make them change form in ways that aren't immediately intuitive. A gas doesn't just become more energetic, it becomes something else entirely, something capable of magnetism, of structured turbulence, of glowing filaments and spirals that stretch for light years. In that way, plasma invites us to think more flexibly about matter. It's not just a progression from solid to liquid to gas to plasma, it's a transformation into a new set of rules. And that shift is worth noticing. It teaches us that matter is dynamic, not static. That the way things behave isn't just about temperature or pressure, but about interactions between particles, between fields, between forces that ripple across scales from atomic to cosmic. Whether it's trapped inside a light bulb or roaring across the surface of a star, plasma is the state of matter that glows with possibility. It's the forgotten fourth, the bright thread running through the fabric of the universe, quietly lighting the way. Imagine taking a group of atoms and slowing them down, slowing them so much that they barely move. Their temperature drops lower and lower until they approach the coldest limit nature allows, absolute zero, where thermal motion grinds nearly to a halt. And then something astonishing happens. The atoms, once individual and independent, start to behave as one. Not metaphorically, as in they're working together, but literally. They merge into a single quantum state, losing their individual identities and acting like one giant unified wave. This is the Bose-Einstein condensate, or BEC for short, and it is one of the strangest and most beautiful states of matter we've ever discovered. To understand why it's so remarkable, we need to tiptoe into the realm of quantum mechanics. At this scale, particles like atoms and electrons don't behave like tiny marbles. They behave like waves. Each particle has a wave function, a sort of mathematical ghost that describes the probability of where it might be and how it might behave. In most situations, those wave functions are all jumbled together, overlapping and interfering like ripples on a pond. But as you cool the system down, the particles lose energy, and their wave functions begin to spread out. Now here's the twist. If the particles are bosons, named after Indian physicist Satyendranath Bose, they're allowed to occupy the same quantum state. Unlike fermions, which obey the Pauli exclusion principle and refuse to share, bosons are the sociable ones. They'll happily pile into the same place, doing the same thing. As the temperature drops and their wave functions spread, they begin to overlap, and once the temperature is low enough, they collapse into a single state. It's not that they're grouped together like peas in a pod, it's that they become indistinguishable. They behave like one enormous atom, a quantum megastructure. This idea was first predicted in the 1920s by Bose and Albert Einstein, long before anyone could even dream of producing such a thing in the lab. The math was elegant, but the technology to test it simply didn't exist. It wasn't until the mid-1990s, over 70 years later, that scientists finally succeeded. Using lasers and magnetic traps, researchers cooled a cloud of rubidium atoms to just a few billionths of a degree above absolute zero. And there it was, the elusive condensate, a brand new state of matter, predicted by theory and born from patience. When atoms form a Bose-Einstein condensate, they move in perfect harmony. Their individual behaviours fade and the collective motion dominates. If you push one part, the whole thing responds. It's like poking a single jellyfish and having the entire ocean wiggle in sync. This unified behaviour leads to some truly bizarre effects. For instance, a beck can flow without friction, a property known as superfluidity. It can even climb up the sides of containers or leak through tiny cracks that would stop any other substance. It doesn't behave like a fluid or a gas or a solid. It behaves like a whispering quantum dream. The creation of Bose-Einstein condensates has opened up a whole new world of experimental physics. Scientists now use them to study quantum phenomena on a macroscopic scale. Things that would normally only be seen in subatomic particles can be observed in entire clouds of atoms. Interference patterns, tunneling, coherence, phenomena that used to live only in equations now exist in glowing clouds of ultra-cold matter. It's a bit like turning a chalkboard diagram into a living, breathing entity. One of the most enchanting aspects of BECS is their ability to exhibit wave-like properties on a visible scale. In one famous experiment, researchers created two separate condensates and then let them overlap. What appeared were interference patterns, regular, repeating light and dark stripes, just like those produced by overlapping water waves or laser beams. Only these weren't photons or ripples in a pond. They were atoms, whole atoms acting like light waves. It was as though matter itself had decided to become a form of radiation. Producing a BEC is no small feat. You can't simply put a flask of gas in the freezer and wait. The temperatures required are just above absolute zero, roughly minus 273.15 degrees Celsius. That's colder than interstellar space. Scientists use sophisticated cooling techniques, including laser cooling, where atoms are slowed by carefully tuned beams of light, and evaporative cooling, where the hottest atoms are allowed to escape, leaving behind the cooler ones. It's like coaxing a crowd into a state of perfect stillness, one atom at a time. And then, once the condensate forms, it's fragile. Any disturbance, any hint of heat or stray energy can cause it to break apart. But in that delicate moment, while it exists, we get a glimpse into the unity of the quantum world, a system where individuality vanishes and the collective motion becomes the only thing that matters. There's also a kind of poetry in the fact that this state is only possible at the lowest temperatures imaginable. As energy drains away, as motion slows, and as randomness fades, nature reveals a new kind of order. The cold brings coherence, stillness brings unity. It's almost meditative, a cosmic quiet where all things move as one. BECS also offer insight into other mysterious systems. They've been used to model early universe conditions, quantum phase transitions, and even simulate black holes on a tabletop. Because they follow quantum rules so precisely, they act like little laboratories for physics at the edge. You can tweak them, measure them, and watch quantum behavior unfold in slow motion is like holding the weirdest parts of the universe in your hand, just a bit colder than usual. And perhaps most delightfully, none of this would have happened without a bit of imagination and a lot of patience. Satyendra Bose, whose work with photons inspired the whole concept, wasn't even trying to discover a new state of matter. He was just curious about how light particles behave when you think of them as indistinguishable. Einstein saw the beauty in the math and extended it to atoms. Decades later, their quiet collaboration blossomed into one of the strangest and most profound discoveries in modern physics. If solids and liquids and gases are the ordinary notes in nature's musical scale, then Bose-Einstein condensates are the deep, resonant hums that you can only hear when the world goes still. They remind us that matter has more to say when it isn't shouting. When atoms whisper together, they reveal the secret harmonies that lie beneath everything we see. Imagine pouring a liquid into a bowl and watching it calmly spread out. Except instead of staying put, it begins to climb up the sides of the bowl, creep over the edge, and spill out onto the table. Not because it's boiling or evaporating or getting pushed around, but because it simply refuses to behave like a normal fluid. It slips through cracks that no ordinary liquid could penetrate. It flows endlessly without slowing down. It doesn't slosh, gurgle, or splatter. It just moves, effortlessly and silently like a ghost made of matter. Welcome to the strange world of superfluids. Superfluids are a class of materials that flow without viscosity. That means they experience no internal resistance, none at all. Viscosity, in everyday terms, is what makes honey slow and syrup sticky. Even water, which seems free-flowing, has some internal friction. Try stirring it in a glass and it resists just a bit. Superfluids, on the other hand, don't resist at all. You can set one in motion and it will just keep going, circling endlessly as if someone forgot to install the brakes. The most famous superfluid is helium, specifically helium-4. When you cool helium down to below about 2.17 Kelvin, which is just a little above absolute zero, it undergoes a phase transition into this bizarre, frictionless state. Scientists call it helium-2. It doesn't look all that different at first glance. It's still a clear, odorless liquid, but its behavior is like nothing else in the universe. For one, it exhibits a phenomenon called the fountain effect. If you insert a tiny capillary tube into a bath of superfluid helium and heat it slightly, helium will climb up the tube and squirt out like a miniature geyser. It's not responding to pressure the way a normal liquid would. It's moving because of differences in quantum energy states. In a superfluid, even a slight imbalance is enough to set off motion that defies intuition. And that climbing the wall trick? That's called roll-in film flow. Superfluid helium can form an ultra-thin layer that crawls up and over the walls of its container. It doesn't stop at the edge. It just keeps going, guided not by gravity or surface tension, but by quantum mechanical rules. It can leak through the tiniest pores in a container and even escape sealed vessels if there's the smallest of imperfections. It's a liquid that refuses to stay still or obey the basic rules of confinement. The underlying cause of all this is quantum mechanics. At temperatures near absolute zero, the helium atoms settle into their lowest possible energy state. But because they're bosons, like the rubidium atoms used to make Bose-Einstein condensates, they can share that state. This results in a kind of collective behavior where the entire liquid acts like one coherent quantum entity. The motion of the fluid becomes quantized, meaning it can only move in specific ways, and it avoids dissipation entirely. There's no friction, no turbulence, no drag. This leads to another strange effect, quantized vortices. If you stir a superfluid, it doesn't form the messy swirls you'd see in a regular fluid. Instead, it forms tiny, stable whirlpools, each one a perfect, discrete unit of circulation. These vortices don't decay over time. They just spin, perfectly maintained, like tiny dancers that never lose rhythm. What's truly astonishing is how long this motion can last. In laboratory conditions, superfluid helium placed in a donut-shaped container has been observed to flow around the loop continuously, without slowing down, for hours, days, even years. There's no measurable loss of energy. It's like winding up a toy car and watching it go forever, without ever coasting to a stop. While superfluidity is most famously demonstrated in helium-4, it can also appear in helium-3, an isotope with one fewer neutron. But helium-3 is made up of fermions, not bosons, so its route to superfluidity is even stranger. It requires the helium atoms to pair up in a way similar to electrons in a superconductor, forming what's called Cooper pairs. This type of superfluid emerges at even lower temperatures, fractions of a Kelvin, and exhibits entirely different properties. It has multiple phases, each with its own internal structure and behaviour. It's as if helium-3 decided that one form of superfluid just wasn't enough. Now, if you thought superfluids were strange, let's go one step further. Supersolids. A supersolid is, in a sense, the paradox child of two opposites. It has the rigid structure of a solid, meaning its atoms are arranged in a regular repeating lattice. But at the same time, it has the ability to flow without resistance, like a superfluid. In other words, it holds its shape and flows at once. For decades, scientists suspected that such a state could exist, but proving it was elusive. Early experiments hinted at it, most famously with helium again, but the data was messy and interpretations were contested. It wasn't until the 21st century, with the help of ultra-cold atoms and precision techniques, that researchers were able to create convincing examples of supersolids in laboratory conditions. In one experiment, physicists trapped a cloud of ultra-cold atoms and induced interactions between them using lasers. The atoms spontaneously organized into a crystal-like pattern, much like a solid, but simultaneously showed signs of coherent motion across the structure. In other words, the atoms knew they were in a grid, but they still flowed. They were moving, but not leaving their place. It's a bit like watching people perform a choreographed dance where everyone stays in formation, yet the whole group glides effortlessly across the floor. This strange behavior comes from a delicate interplay between quantum mechanics and interactions among particles. In supersolids, atoms arrange themselves into a structure not just because of packing efficiency, but because of the waves associated with their quantum states. These waves overlap and interfere in ways that create a repeating pattern of density, like a crystal, but allow for motion within the pattern. It's a state that seems to challenge our very language. How can something be solid and fluid at the same time? And yet nature doesn't mind contradictions, especially at the quantum level. In fact, it thrives on them. Superfluids and supersolids are a reminder that the behavior of matter is deeply contextual. The same atoms that bounce around freely at room temperature can settle into perfect quantum harmony when cooled. The same helium that fills party balloons can flow through walls or spin without end if you treat it just right. These materials also hold promise for technology. Understanding superfluidity helps in developing more efficient cooling systems and could play a role in quantum computing, where the preservation of coherent states is vital. Supersolids, still a newer frontier, might help us understand collective quantum behaviors in new ways, and maybe even lead to novel materials that challenge what we think solids and fluids can do. But even without the practical angle, there's something deeply mesmerizing about these states of matter. They are the poetry of physics, substances that defy friction, that remember their place while flowing freely, that respond to the softest push with an elegant, endless motion. They remind us that matter is not merely what we see or touch, but how particles relate, how energy shapes behavior, and how quiet, ordered motion can exist even in the coldest corners of the universe. In the end, superfluids and supersolids are not just scientific curiosities, they're glimpses into a deeper reality, a reality where the rules bend, where motion continues without end, and where structure and flow are not opposites, but partners in a graceful quantum dance. Imagine rewinding the universe, not just back a few centuries or even a few million years, but all the way, back before stars, before atoms, before even protons and neutrons had found their footing. We're talking about the first few microseconds after the Big Bang. During this time, the universe was so hot, so dense, and so intensely energetic that the matter we're familiar with couldn't exist. Instead of neat particles and tidy structures, everything was dissolved into a wild, chaotic soup called quark-gluon plasma. To understand this exotic state, we need to zoom in deep, deeper than atoms, deeper than the protons and neutrons that make up atomic nuclei. Protons and neutrons themselves are made of smaller particles called quarks, which are held together by the strong nuclear force. That force is carried by particles known as gluons. Quarks and gluons don't usually roam free. Under normal conditions, they're tightly bound inside hadrons, the family of particles that includes protons and neutrons. It's a bit like trying to separate drops of honey from a thick tangle of cobwebs, nearly impossible under everyday circumstances. But when temperatures soar to several trillion degrees, yes, trillion with a T, something dramatic happens. The binding breaks, the quarks and gluons break free from their confinement and move independently in a high-energy soup. This is quark-gluon plasma, a phase of matter so extreme that it can only be created under conditions resembling the early universe itself. It's not just hot, it's the hottest substance we know how to make. In fact, when scientists recreated it in particle colliders, they achieved temperatures over 4 trillion degrees Celsius, hotter than the core of any star. This plasma is unique not only because of its composition, but also because of its behavior. You might expect a substance made of high-energy, unbound particles to behave like a gas, chaotic, turbulent, and completely disorganized. But quark-gluon plasma doesn't play by those rules. Instead, it flows like a perfect liquid with near-zero viscosity. That means it moves smoothly, without resistance, even better than superfluids under ultra-cold conditions. It's a curious twist of nature. Take the hottest material in the universe, and it turns out to be one of the smoothest flowing, most elegant forms of matter we've ever seen. Creating quark-gluon plasma on Earth isn't something you do in a regular lab. It takes gigantic machines like the Large Hadron Collider at CERN or the Relativistic Heavy Ion Collider in New York. These machines accelerate heavy ions, such as gold or lead nuclei, to nearly the speed of light, then smash them together. In that instant of collision, for just a fraction of a second, the energy density becomes so immense that the protons and neutrons melt, releasing their quarks and gluons into a fleeting miniature version of the early universe. It's like building a time machine powered by subatomic fireworks. Studying these fleeting droplets of primordial plasma gives us an extraordinary window into the conditions that shape the cosmos. By analysing how the plasma flows, how it expands and how it cools, scientists can reconstruct what happened in those first tiny moments after the Big Bang. It helps us understand not only how matter formed, but why it formed the way it did. One of the most intriguing mysteries it helps to explore is why the universe has more matter than antimatter. According to the standard model of particle physics, the Big Bang should have created equal amounts of both. Yet when we look around, we're clearly living in a matter-dominated universe. The processes inside quark-gluon plasma could hold some of the clues. Subtle differences in how particles interact at these energies might explain how that imbalance arose, allowing matter to win and the universe to grow instead of annihilating itself in a flash of perfect symmetry. Another interesting aspect is that quark-gluon plasma doesn't stick around. It cools rapidly, within microseconds, and begins forming the building blocks of matter. As it loses energy, quarks start pairing up, pulled together again by the strong force, and the familiar zoo of hadrons begins to emerge. Protons and neutrons are among the earliest to form, and from there, the universe begins its long journey toward atoms, stars, and eventually life. In a very real sense, quark-gluon plasma is the womb from which everything we know was born. It's poetic, really. the densest, hottest chaos gives way to the structured calm of particles, which then build the order of galaxies, planets, and people. But that primal fire never fully vanished. Some theories suggest that remnants of quark-gluon plasma may still exist in extreme cosmic environments, inside neutron stars, for example, or in the cores of the most powerful explosions in the universe. If you dig deep enough, the early universe may still echo in the heart of a dying star. There's even speculation about quark stars, hypothetical objects denser than neutron stars, where the pressure is so immense that even neutrons break down into a sea of quarks. These stars, if they exist, would essentially be cosmic droplets of quark matter, frozen snapshots of the universe's infancy. They've not been confirmed, but the search is ongoing. In the grand tradition of physics, the more we learn, the more the universe seems willing to offer new surprises. In recreating and studying quark-gluon plasma, scientists are not just probing the past, they're testing the boundaries of what matter can be. It's an effort to understand the rules that governed the very first moments of existence, when nothing yet had shape or name, and everything that would ever be was still just potential, swirling in a soup of unbound energy. And let's not forget the role of gluons. They don't just carry the strong force, they are the glue. Their name isn't a coincidence. Without gluons, quarks would drift apart, never forming the protons and neutrons that build atoms. The strong force they represent is incredibly powerful, over 100 times stronger than the electromagnetic force, but it only acts at extremely short distances. Within quark-gluon plasma, that force loosens just enough to allow the particles to roam free. But the moment energy levels drop, the force snaps back, reeling the quarks into tight bundles again. It's like an elastic band stretched to its very limit. Relax the tension, and everything snaps shut in a blink. It's humbling to think that the stuff we're made of, protons and neutrons, weren't always around. They are, in a sense, condensed survivors of a much wilder past. And while we walk around comfortably at 20 degrees Celsius, the matter that makes us was forged in fire hotter than anything we can imagine. It's like finding out your family tree begins with a lightning storm in a volcano. Quark-gluon plasma may be fleeting, invisible to the eye, and buried in the depths of particle collisions, but its importance can't be overstated. It holds the story of how the universe cooled into structure, how energy became matter, and how chaos gave birth to order. It is the closest thing we have to a portrait of the cosmos before it settled down, a moment when everything was free, fast, and impossibly hot, waiting to become something more. Imagine a pendulum swinging back and forth forever, not because you're winding it up, not because it's slowly draining energy from a battery or a spring, but because it's doing it all on its own, endlessly, without losing energy. At first glance, that might sound like a physics fantasy, maybe even a violation of the sacred laws of thermodynamics. Perpetual motion. That's firmly in the land of impossible machines and hopeful inventors. And yet, in the strange world of quantum physics, something eerily similar does exist. Time crystals. Time crystals are one of the newest and most bizarre phases of matter ever discovered. The name might sound like something out of science fiction, but they are very real and very strange. These are structures that don't just repeat in space like ordinary crystals, they also repeat in time. That is, their internal states change in a rhythmic, cyclic pattern, even in their lowest energy configuration. They essentially tick on their own, without burning through energy. A kind of quantum clockwork, endlessly turning in the silence of zero motion. To appreciate how weird this is, it helps to first understand what a normal crystal is. Take a diamond or a snowflake. Their atoms are arranged in repeating patterns in space. That's what gives crystals their structure and symmetry. Walk through the lattice of atoms and you'll see the same pattern repeating over and over, but once they reach their lowest energy state, their ground state, they stop changing. They just sit there, perfect and still. Time crystals, on the other hand, keep moving. Even in their ground state, they cycle between configurations in a perfectly regular rhythm. It's like shaking a snow globe and then discovering the snow never stops falling. It just loops over and over forever. Except you didn't shake it. It started looping all by itself. The idea of a time crystal was first proposed in 2012 by Nobel laureate Frank Wilczek. At the time, it was just a theoretical curiosity, a playful thought experiment. Could time, like space, have a crystalline structure? Could a system exhibit periodicity not in where its atoms are, but in how they evolve over time? The proposal sounded bold, maybe even a little outlandish. After all, physicists are very protective of their energy conservation laws. Anything that sounds like perpetual motion sets off a lot of alarm bells. But Wilczek's idea was more subtle. He wasn't proposing a machine that creates energy from nothing. He was suggesting that certain systems might have an internal rhythm that persists in time, without the need for added energy, because of how quantum systems behave at extremely low temperatures or under very specific conditions. It would be motion, yes, but not the kind that violates any laws. It would be more like a frozen dance, always moving but never expending anything. For a while, time crystals remained theoretical. But then, in the late 2010s, a series of breakthroughs began to turn theory into reality. Using chains of trapped ions, laser pulses, and carefully controlled quantum systems, researchers were able to create what they called discrete time crystals. These systems were periodically driven, nudged at regular intervals, and instead of simply following the rhythm of the input, they responded at a different, stable rhythm. Like tapping your finger on a table every 2 seconds and having the table respond with a beat every 4 seconds. Forever. The time crystal found its own tempo and stuck with it. This is important because it means the time crystal isn't just passively riding along with the energy you feed it. It locks into a kind of subharmonic response, repeating in time independently. And remarkably, this pattern doesn't fade. In an ordinary system, small imperfections or thermal energy would eventually cause things to settle down. But in these quantum systems, the pattern persists, seemingly immune to decoherence. It's like a metronome that never winds down, even when you stop playing music. These discoveries were made using highly controlled quantum environments. Google's quantum computing team, for example, used their Sycamore processor, essentially a collection of superconducting qubits, to create a time crystal by applying a specific sequence of operations that caused the system to flip between states at a steady pace, without losing energy to the environment. It's like programming a quantum flipbook that never runs out of pages. What's fascinating is that these systems must be periodically driven. That is, they aren't completely isolated. But they don't absorb energy in a normal way either. Instead, they enter what's called a many-body localized state, where the energy input doesn't heat the system up, but rather helps sustain its rhythmic motion. It's a bit like tapping a drum just hard enough to keep a rhythm going, but not so hard that the drum gets louder or changes tone. This idea that you can have motion without energy loss in a stable, repeating pattern challenges our classical understanding of equilibrium. In traditional physics, the ground state is static. Time crystals break that intuition. They show us that quantum systems can have dynamic ground states, where movement is not just possible, but built into the very fabric of the lowest energy level. From a practical standpoint, time crystals are still in their infancy. They're not going to power your phone or run your toaster anytime soon, but they represent a completely new way of thinking about matter, time, and stability. In a world increasingly shaped by quantum technologies, that kind of novelty matters. These exotic phases could one day play a role in quantum computing or information storage, particularly in maintaining coherence over long periods. Because time crystals resist certain types of noise and disorder, they could offer new tools for preserving delicate quantum information. There's also something philosophically beautiful about time crystals. They invite us to reconsider what we mean by stillness. Traditionally, we associate stability with a lack of motion. A crystal is stable because its atoms are fixed in place. A pendulum at rest is stable because it doesn't move. But a time crystal says no. Motion itself can be stable. Repetition can be order. Change can be the constant. It flips our instincts on their head, showing us that equilibrium doesn't have to mean silence. Sometimes it can mean rhythm. The idea of motion without energy loss isn't entirely foreign. Superfluids do something similar, flowing forever without resistance. But time crystals are more fundamental. Their motion is internal, rhythmic, and not tied to spatial movement. It's not a flow, it's a pulse. A quiet heartbeat at the heart of a quantum system. If this all sounds too perfect to be true, it's worth remembering that time crystals don't violate the laws of physics. They work within them, using quirks of quantum mechanics, symmetry breaking, and precise engineering to do something we never thought matter could do. They're not magic, but they are magical. Tiny loops of eternal motion, ticking away in the hidden corners of the quantum world. Time crystals aren't made of time. They don't let you travel through it, and they won't show up in your local geology museum. But what they represent is perhaps even more fascinating. A new way for matter to organize itself. A new form of persistence. A reminder that the universe still has surprises waiting for those who listen carefully enough to hear its quiet, repeating rhythm. There's something delightfully mischievous about ketchup. You tip the bottle, give it a gentle shake, and nothing. Then, with a little more encouragement, it finally lets go and splatters all over your plate in one unruly glob. It's not just being difficult for the fun of it, though it sometimes feels that way. Ketchup, along with toothpaste, slime, custard, and a host of other everyday substances, doesn't follow the tidy rules of physics that govern normal liquids. These are non-Newtonian fluids, and they're here to challenge everything you thought you knew about how matter should behave. Let's start with Sir Isaac Newton, who gave us the classical laws of motion, and, more relevant here, a neat little rule for fluids. According to Newtonian physics, a fluid has a constant viscosity, meaning that its resistance to flow stays the same no matter how much force or stress you apply. Water, for example, flows smoothly, whether you pour it gently or stir it vigorously. It doesn't get thicker or thinner based on how hard you push. That's Newtonian behaviour, but not all fluids play by those rules. Non-Newtonian fluids are materials whose viscosity changes when force is applied. Some get thicker, some get thinner. Some behave like solids until you poke them, and others act like liquids until they're squeezed. It's all very confusing and, frankly, a little magical. But there is real science behind the mess. Take oobleck, for instance, a simple mixture of cornstarch and water that you can make in your own kitchen. When you stir it slowly, it behaves like a liquid, oozing and dripping with no resistance. But when you slap it or try to punch it, it fights back. It hardens instantly and can even crack under stress. If you fill a shallow tray with the oobleck and run across it quickly, your feet bounce off the surface as if it was solid. Stand still though and you'll slowly sink in. It's part liquid, part trap, and completely fascinating. This strange behaviour comes from the way the tiny cornstarch particles are suspended in water. When left undisturbed, the particles can slide past one another easily, letting the mixture flow. But under sudden force, the particles are jammed together, locking into a temporary structure that resists motion. It's called shear thickening, a fluid that gets thicker the harder you push it. You can think of it as a crowd of people in a hallway. If everyone's walking slowly, there's room to pass. But if someone starts sprinting, people get in the way and everything clogs up. On the flip side, some non-Newtonian fluids do the opposite. They exhibit shear thinning, where viscosity decreases with stress. Ketchup is a perfect example. When it's just sitting there in the bottle, it's fairly thick. But once you start shaking or tapping it, the internal structure breaks down and it flows more easily. Toothpaste and paint behave in a similar way. You don't want paint to drip all over the place when you're not using it, but once you roll it on a wall, it needs to spread smoothly. These materials are engineered to behave differently under stress, and it makes them incredibly useful, and occasionally frustrating. Then there are viscoelastic materials which blur the line between solids and liquids even further. Slime is a perfect case. It stretches slowly if you pull gently but snaps if you tug too quickly. It can hold its shape for a while but eventually slumps into a puddle. This behavior comes from long-chain polymers, molecules that are tangled together like a microscopic bowl of spaghetti. These chains can uncoil and move under gentle stress, but if you move too quickly they resist and bounce back. It's part liquid, part elastic, and entirely entertaining. Gels take things one step further. A gel is mostly liquid, but it behaves like a solid. Hair gel, jelly, and gelatin desserts are all made up of liquid molecules trapped in a network of solids, usually held together by chemical bonds or physical entanglements. The result is a substance that holds its shape, wobbles when disturbed, and can transition between solid and liquid behavior depending on the conditions. The water in a gel is technically free to move, but it's corralled by the structure it's embedded in, like dancers moving freely, but only within the bounds of the choreography. Amorphous solids also belong to this family of structurally confusing materials. Unlike crystals, where atoms are arranged in orderly repeating patterns, amorphous solids lack long-range order. Their atoms are jumbled, disordered, and without symmetry, much like a liquid that got stuck midway through freezing. Glass is the most famous example, but others include plastic, wax, and certain types of rubber. They don't flow like liquids, but under the right conditions, extreme heat or pressure, they can deform, sag, or even flow slowly over time. Their solidity is not absolute, it's conditional. Even biological materials can behave in non-Newtonian ways. Blood, for example, is a complex fluid that changes viscosity depending on flow conditions. It's shear thinning, meaning it flows more easily in narrow blood vessels where it's needed most. This property allows it to navigate the body efficiently, adjusting itself as it moves through veins and arteries. Egg whites, saliva, and mucus are also non-Newtonian, giving our bodies a surprisingly squishy relationship with fluid mechanics. One of the most captivating things about these materials is that they're so common, yet so counterintuitive. They're not rare or exotic. They're in your refrigerator, your bathroom, your body. You've probably interacted with a dozen non-Newtonian substances today without realizing it. That moment when you squeeze shampoo out of a bottle and it suddenly gushes. That's shear thinning. When you walk across wet sand and it firms up beneath your feet. That's a type of stress-induced solidification. These materials hide in plain sight, quietly breaking the rules when no one's looking. Scientists and engineers take full advantage of these properties. Body armor that hardens on impact is often made from shear thickening fluids. The material is flexible under normal conditions but becomes rigid when struck, helping absorb energy from impacts. Sports padding, helmets, and even protective gear for astronauts have been developed using similar principles. In the industrial world, non-Newtonian fluids are used to control flow rates, reduce spatter in coatings, and create textures that would be impossible with ordinary liquids. The unpredictability of these materials also makes them useful in research. They help scientists understand how internal structure affects flow behavior, a field known as rheology. Rheologists study how matter deforms and flows under different conditions, and they rely heavily on materials that bend the rules. From studying earthquake dynamics to designing new food products, understanding these squishy, stretchy, sticky substances has enormous value, and they're just fun. There's something undeniably satisfying about playing with slime or smacking a bowl of oobleck. It taps into that basic human curiosity, the joy of squish, the thrill of unexpected resistance. These materials feel alive in a way that static solids and simple liquids don't. They respond, they adapt, they surprise. It's science with personality. In the bigger picture, non-Newtonian fluids and amorphous materials show us that the states of matter aren't rigid categories. They're more like tendencies. Water tends to act like a liquid, yes, but under the right conditions, even a liquid can stand its ground. A solid can lose its shape. A gel can dance between firmness and flow. These materials remind us that behavior is often more revealing than labels. Nature rarely fits into boxes, and these substances are proof. They bend, twist, resist, and yield, all depending on how you treat them. They teach us that force and flow are not always straightforward, that the same push can yield different results depending on the context. It's a gentle reminder that the universe is full of nuance, even in something as seemingly simple as a bottle of ketchup or a bowl of goo. In the end, these slimes, gels, and goops offer more than just a messy diversion. They reveal the quiet complexity of the world around us. Beneath their playful textures lie deep scientific truths about structure, energy, motion, and the ways materials respond to the forces we often take for granted. They're not just curiosities, they're invitations to look closer, touch gently, and ask the kind of questions that only begin with, "Why does this feel so weird?" Let's begin with something simple, a donut and a coffee mug. Despite their very different uses at breakfast time, in the strange world of topology, they're considered the same, not because physicists have gone mad, but because they each have exactly one hole. A donut has its central hole, and a mug has the hole in the handle. Topology doesn't care about shapes in the usual sense. It cares about properties that remain unchanged when you stretch, twist, or bend something, as long as you don't tear it or glue it together. That idea, which sounds whimsical at first, turns out to have profound consequences for matter itself. Welcome to the world of topological phases, where the geometry of quantum systems gives rise to behavior so strange, they make superconductors seem positively old-fashioned. These phases of matter aren't defined by symmetry or crystal structure, but by how their quantum states wrap around, twist, or loop through abstract mathematical spaces. They hold memory, not in bits and bytes, but in the very shape of their wave functions. The idea of topology influencing matter began to take hold in the 1980s with the discovery of the quantum Hall effect. When researchers placed a two-dimensional sheet of electrons into a very strong magnetic field at extremely low temperatures, they observed something completely unexpected. The electrical conductivity didn't vary smoothly with the magnetic field strength, as one might expect. Instead, it changed in perfectly quantized steps. Each jump represented a whole number increase, with mind-bending precision, accurate to more decimal places than just about anything else in physics. Why was this happening? The answer lay not in ordinary mechanics, but in topology. The electrons' wave functions were wrapping around in ways that could be described using topological invariants, essentially mathematical numbers that remained fixed no matter how the system was deformed. These numbers explained why the conductance jumped in discrete steps, and why those steps were so robust. You could scratch the surface, shake the system, or add small impurities, and the quantized effect wouldn't budge. It was like trying to undonut a donut without removing the hole. The system's topology preserved its essential nature. This discovery opened the floodgates to a whole new class of materials, topological insulators. These are materials that behave like insulators in their interior, meaning electrons don't flow easily through the bulk, but conduct electricity flawlessly along their surfaces or edges. Imagine a chocolate truffle that's insulating on the inside, but with a delicate outer shell that zips electricity along like a copper wire. This edge conductivity isn't just convenient, it's protected by the topology of the system. You can rough up the edges, introduce imperfections, or deform the shape, and the conductivity remains, because the underlying topological structure hasn't changed. In more familiar phases of matter, properties arise from symmetry breaking. Think of how ice forms a crystalline structure, or how a magnet aligns its spins. Topological phases, by contrast, don't need broken symmetry. Their defining feature is global, a kind of holistic quantum entanglement that gives the system stability and resilience. This makes them ideal candidates for applications like quantum computing, where the goal is to store and manipulate information in ways that are resistant to noise and error. One of the most exotic manifestations of topological phases is the emergence of quasi-particles with fractional charges. In certain systems, especially those exhibiting the fractional quantum Hall effect, electrons appear to split into smaller, fractionally charged components. These are not fundamental particles like electrons or quarks, but emergent phenomena, patterns of collective behaviour among many particles. It's a bit like a stadium wave. No single person is moving around the stadium, but the pattern travels as if it's a single entity. These quasi-particles can carry charges of 1/3 or 1/5 of an electron's charge, depending on the system. Even more astonishing are the theoretical predictions of anyone's, quasi-particles that exist only in two-dimensional systems and that don't behave like fermions or bosons, the two traditional categories of particles. When you swap two fermions, like electrons, their wave function changes sign. When you swap two bosons, like photons, their wave function stays the same, but swap two anyons, and their wave function can twist into something entirely new. These exotic behaviours are tied to the topology of the space they live in. Anyons could be the key to topological quantum computers, machines that use braids of particle paths to store and manipulate information in ways that are naturally immune to tiny errors. What makes topological phases especially enchanting is their invisibility. You can't see the topology with a microscope. The atoms don't rearrange into a distinctive pattern. The magic is in the mathematics, hidden in how the quantum states wind and twist through abstract dimensions. It's like finding out your living room has a secret door not in physical space, but in how your furniture resonates with the fabric of the universe. Topological phases also defy easy classification. In the periodic table of matter, they don't fit neatly into columns. They require an entirely different framework, one that combines condensed matter physics, quantum mechanics, and pure mathematics. This interdisciplinary nature is part of what makes them so exciting. They're where geometry meets electricity, where wave functions become loops, and where structure is defined not by where particles are, but by how they behave when you try to move them around. In three-dimensional materials, topological effects still occur, but they become more intricate. You might find surface states that conduct electricity only on specific faces, or materials that host exotic spin textures called skyrmions, tiny whirlpools of magnetic orientation that behave like particles. These textures are topologically protected too, meaning they're hard to destroy and can even be used to store information in magnetic memory devices. One compelling feature of these systems is their robustness. Unlike ordinary conductors, which can lose performance when damaged or exposed to impurities, topological materials resist such degradation. Their properties are baked into their topology, which is not easily disturbed. This resilience makes them highly attractive for future technologies. In a world increasingly reliant on stable, error-resistant systems, topological phases offer something genuinely new, performance rooted not in perfection, but in the stubborn, twisty logic of quantum geometry. The study of topological matter is also expanding beyond electrons. Photons, for example, can be manipulated in carefully structured optical materials to mimic topological behaviours. The result is topological photonics, a field exploring how light can be guided around corners, past obstacles, or through waveguides without backscattering or loss. Similar ideas are being applied to sound waves in topological acoustics, and even to mechanical systems that exhibit protected modes of vibration. Topology, it seems, is not limited to the quantum world. Its reach spans across scales and phenomena, showing up wherever waves, fields, and geometry collide. And all of this began with a simple question. What happens when we stop looking at matter as a collection of particles and start thinking about the shapes their behaviours form in abstract space? The answer, it turns out, is a wonderland of new phases, exotic particles, and deeply counterintuitive properties. In topological phases, matter has memory. Not memory like a flash drive, but memory of how it's been twisted, turned, and shaped in a space that defies ordinary sight. It remembers not where it's been, but how it moved. And in that memory lies a kind of resilience, a secret strength woven into the quantum fabric. It's a reminder that matter, like meaning, is sometimes hidden in the patterns between things, in the relationships, not the pieces. The universe, through topology, whispers that structure doesn't always come from what we see, but from how things connect. And in those connections, those invisible loops and twists, we find an entirely new way of understanding what matter can be. If you're listening to this through a smartphone or watching it on a flat panel screen, you're already staring into one of the strangest and most beautiful states of matter ever discovered. The screen you hold, smooth, colourful and quietly humming with light, is powered by a material that flows like a liquid but arranges itself like a crystal. It's neither here nor there, it lives in between. It is, as the name suggests, a liquid crystal. Liquid crystals are a study in contradiction. They are materials that blur the line between order and freedom. Their molecules aren't locked into rigid positions like in a solid, but they're not totally free to roam around like in a regular liquid either. Instead, they exhibit a kind of soft structure, a compromise, if you will. Their centres of mass are mobile, allowing them to flow, but their orientation, how they're angled or aligned, tends to follow a pattern. It's a kind of elegant choreography, where the dancers move across the stage, but keep facing the same direction. At the heart of most liquid crystals are rod-shaped molecules, long and narrow like microscopic needles. When these molecules are heated above a certain temperature, they enter a state where they begin to move around more freely, much like molecules in a typical liquid. But even as they flow, they tend to stay lined up, pointing roughly in the same direction. This directional order, even in the midst of motion, is what makes them so fascinating. This alignment isn't just a curious feature, it's central to how liquid crystals function in everyday devices. In a liquid crystal display, or LCD, the molecules can be manipulated with electric fields. When you apply voltage, the orientation of the molecules shifts. That change in orientation affects how light passes through the material, whether it gets twisted, polarized, blocked, or allowed to shine through. By controlling the alignment of these molecules in tiny pixel-sized regions, screens can form images, show text, or play videos. Every letter you read and every picture you see on an LCD screen is made possible by molecules doing a carefully choreographed dance in unison. But let's back up for a moment. Long before liquid crystals found their way into our gadgets, they were simply an oddity in the laboratory. The phenomenon was first observed in the late 19th century by Austrian botanist Friedrich Reinitzer, who noticed something strange while heating a substance derived from cholesterol. It didn't transition directly from solid to liquid, as most materials do. Instead, it passed through an intermediate cloudy phase. This behaviour baffled scientists at the time, until further work revealed that the material was entering a new state, something between solid and liquid. It wasn't fully understood, but it was clear that this wasn't ordinary melting, it was something altogether new. Eventually scientists began classifying these intermediate phases, and today we recognise several distinct types of liquid crystal phases. The most common is the nematic phase. In this state the molecules are aligned in the same general direction, but their positions are random, like matchsticks floating in water, all pointed roughly the same way but not arranged in a grid. The word nematic comes from the Greek word for thread, because under polarized light, these substances often look like a tangled network of fine lines. Then there's the smectic phase. Here the molecules not only align directionally, but also begin to stack into layers. They can still flow within those layers, but the structure becomes more refined, more like a stack of sliding sheets. This added order gives smectic phases unique properties, such as elasticity and viscosity that vary depending on direction. And then there are clysteric or chiral nematic phases, where the orientation of the molecules twists gradually as you move through the material, forming a helical structure. This twist reflects certain wavelengths of light, giving rise to iridescent colours. This property is what makes liquid crystal coatings useful for temperature-sensitive applications, like mood rings and thermometers that change colour as they warm or cool. Even in nature, liquid crystals abound. The structure of cell membranes, for instance, is remarkably similar to certain liquid crystal phases. Some biological tissues, including the layers in your eyes, exhibit liquid crystalline behavior. The shapes and alignments of molecules in these systems are not entirely rigid, but they're not disordered either. It's a balance, enough structure to maintain form, enough freedom to allow function. What makes liquid crystals so enthralling from a scientific point of view is how they demonstrate that order and fluidity aren't mutually exclusive. Most of us are taught to think of solids as structured and immobile, and liquids as unstructured and free-flowing. Liquid crystals remind us that matter is more versatile than that. It's not always about choosing sides. Sometimes matter prefers the middle ground. Their responsiveness to external fields is another defining trait. Because the orientation of their molecules can be influenced by electric or magnetic fields, liquid crystals can be tuned. This tunability means that with just a small amount of energy, you can dramatically alter their optical properties. That's why they're so energy efficient when used in screens. They require very little power to change state, and once set, they can hold that state until prompted to shift again. The interplay of light and liquid crystals is an entire field of study in itself. Their ability to manipulate polarization makes them ideal for not just displays, but also lenses, optical filters, and even experimental physics setups. Light travelling through a liquid crystal can be twisted, slowed, or redirected in ways that wouldn't be possible with ordinary materials. It's a kind of invisible art. Molecules arranging themselves just so to guide photons in a specific direction. There's also a meditative elegance to liquid crystals. In their natural state, they resemble serenity. They hold a form, but not too tightly. They move, but not chaotically. They seem to understand something about balance that we often forget, that it's possible to be aligned without being rigid, and to be in motion without being unruly. In many ways, they're the physical embodiment of graceful compromise. Their scientific complexity hides beneath a calm surface. Behind every TV screen and digital watch is a matrix of tiny droplets, each one containing molecules standing in formation like tiny sentinels, ready to pivot at the flick of a switch. It's as though millions of little compass needles are constantly realigning, quietly enabling the stream of images and data we consume every day. And yet, for all their technological use, liquid crystals are also deeply mysterious. Researchers are still uncovering new phases, discovering how these materials behave under extreme conditions, and exploring their potential in fields far beyond displays. Some are studying how they could be used in soft robotics, where materials can flex and change shape without rigid motors or hinges. Others are using liquid crystals to build sensors that detect subtle environmental changes, or to investigate how biological tissues grow and heal. They are not just tools or materials, they are puzzles. Each molecule's alignment carries information about its surroundings, about temperature, pressure, and electromagnetic influence. Collectively, they form systems that are sensitive, dynamic, and surprisingly self-aware, in the way only nature's finest arrangements can be. In a world that often pushes us to choose between order and freedom, liquid crystals offer a gentle alternative. They exist in between, in a place where structure meets softness, and motion finds meaning without losing its shape. They don't fight their dual nature, they embody it, and perhaps that's why they've become such an essential part of our daily lives. Not just because they help us see, but because they help us imagine what it means to hold a form, even while flowing through it. Ice, in its everyday form, is a reassuringly simple thing. It clinks in glasses, cracks underfoot, and melts quietly into puddles. We think of it as water's solid, sleepy cousin, a phase as familiar as snowflakes or frozen peas. But beneath that frosty exterior lies a world far stranger than most people ever realize. Ice, it turns out, is not a single substance, but a whole family of structures. Scientists have identified at least 19 distinct types of ice, each with its own internal arrangement of water molecules. And that's not even counting the theoretical ones still being explored. Even the most ordinary of substances, when placed under the right pressure or chilled to the right temperature, becomes a playground for strange geometry and unexpected behaviour. The kind of ice we're most familiar with is known as ICE-H. That H stands for hexagonal, because in this form, water molecules arrange themselves in a six-sided pattern. This is the stuff of snowflakes, frost and ice cubes. Beautifully ordered, but relatively boring as far as the molecular world is concerned. The reason ice floats on water is because the hexagonal lattice holds the molecules relatively far apart, making the structure less dense than the liquid. This is an unusual property. Most substances are denser in their solid form. But water, always the overachiever, has to be the exception. But venture outside the narrow band of temperature and pressure where Ice-1H lives, and water begins to reinvent itself. Push the pressure up, or the temperature down, or both, and the molecules start rearranging into entirely new patterns. These alternate forms of ice are given Roman numerals, 1, 2, 3, all the way to 19 so far. Each one has a unique crystal structure, like different architectural blueprints for stacking water molecules. Some of these ices are denser, some are more compact, and some exhibit symmetry so bizarre you'd think they were drawn up by an architect on a sugar rush. Take Ice 2, for example. It forms under higher pressures and is more tightly packed than ordinary ice. Its molecules are arranged in a rhombohedral lattice, a sort of squished, skewed box pattern. Then there's Ice V and Ice VE, which form under even more pressure, squeezing the water molecules into increasingly awkward and intimate configurations. Ice 7 is particularly famous because it can exist at high pressures and even high temperatures, making it relevant in the study of planets and moons, with thick, icy crusts and hot interiors. Deep beneath the surface of Jupiter's moon Europa, or in the high-pressure mantle of an exoplanet, Ice 7 could be forming as we speak, dense and strong and entirely alien. There's also Ice 11, which is a ferroelectric phase. That means it has a built-in electric polarity. Its molecules don't just sit still, they align their dipoles in a common direction, creating a tiny internal field. It's like the ice is trying to become a battery. Ice 12, on the other hand, is formed through sudden pressurization at low temperatures, and exists in a metastable state. It's a reminder that even ice can be caught off guard and locked into a phase it wasn't quite planning to be in. These exotic ices have practical implications as well as theoretical charm. Understanding their structures helps scientists model the interiors of icy moons, predict how water behaves under extreme conditions, and even explore the limits of hydrogen bonding, which governs not just ice but much of the chemistry of life. It also leads us into the realm of materials science, where the way molecules arrange themselves can determine everything from strength to conductivity. But even ice's weirdest forms look positively straightforward compared to what happens when you try to freeze helium. Helium is the lightest noble gas, and it's notoriously slippery. At room temperature, it's a gas. Cool it down, and it becomes a liquid, but one that refuses to solidify under normal pressure. Even near absolute zero, helium won't form a solid unless you apply tremendous pressure, tens of thousands of atmospheres. It's a bit like trying to convince a very relaxed cat to stand at attention. It doesn't want to conform, and it takes a lot of coaxing to make it change states. Solid helium exists, but it's not easy to create or study. When forced into a solid form, it forms a crystal lattice just like other substances, but with some unusual properties. The atoms remain incredibly mobile within that lattice. There's evidence that they might exhibit quantum effects like tunneling, where they shift position without going over an energy barrier. In fact, solid helium has been at the center of debates about whether supersolidity, a phase where a solid flows like a superfluid, could be real. While the most dramatic claims of supersolid helium have been walked back or revised, the fact remains. This is no ordinary crystal. Helium's refusal to freeze under typical conditions is due to its quantum zero-point energy. That's the lowest possible energy a quantum system can have. And for helium, that baseline jitter is strong enough to keep it from settling down into a solid structure. The atoms vibrate so energetically, even near absolute zero, that the attractive forces can't hold them in place without the assistance of pressure. It's like trying to build a tower of jello cubes during an earthquake. They just won't stay still long enough to stack. When it finally does become solid, helium offers physicists a unique opportunity to study quantum mechanics on a macroscopic scale. Its behavior is so dominated by quantum effects that it behaves less like a traditional solid and more like a collective of harmonizing wave functions. This makes it a kind of window into a world where matter doesn't behave the way we expect, even when it's technically frozen. Other substances also show exotic solid behavior. Methane and ammonia, for instance, form a variety of crystalline structures under pressure, some of which might exist in the interiors of gas giants or icy exoplanets. There's even growing interest in superyonic ice, where the hydrogen ions become mobile within an otherwise solid oxygen lattice. This phase could exist inside Neptune or Uranus, and it's both solid and liquid at once, a kind of electrified flowing crystal. It's as if the material couldn't decide whether to be stable or mobile and simply chose both. All of this complexity emerges from a molecule as simple and familiar as water. 2 hydrogens, 1 oxygen. A slight bend in the angle, a dipole moment, and suddenly we're dealing with a substance that has more solid forms than most elements have ever dreamed of. Water's ability to form hydrogen bonds, a kind of gentle but persistent molecular handshake, makes it uniquely adaptable. It can be open and airy or tightly packed. It can trap gas molecules inside its lattice, forming clathrate hydrates. It can even become amorphous, like a frozen glass, with no crystal structure at all. The study of ice, in all its forms, isn't just about understanding frozen water. It's about learning how matter organizes itself under pressure, how temperature and energy influence structure, and how even simple substances can surprise us when we look closely. Ice is not a static, passive state. It's an active, dynamic participant in the molecular world, constantly negotiating with energy, environment, and entropy. And perhaps that's the real beauty in all of this. What we think of as solid, stable, and fixed is actually a universe of variation. Ice isn't just one thing. It's a language of form, a vocabulary of molecular positions, all spoken by the same 3 atoms in different rhythms. And helium, playful, reluctant helium, reminds us that even freezing isn't universal, that some things just don't want to settle, no matter how cold they get. When we look at a snowflake, we're not just seeing frozen water, we're seeing one possible answer to a question that has a dozen stranger answers waiting in the wings. All it takes to find them is a little pressure, a lot of patience, and the willingness to believe that even the most familiar things still have secrets hidden under the surface. Out in the quiet spaces between stars, where the night sky stretches deeper than any horizon, the matter of the universe drifts, floats, and pulses in forms that rarely resemble anything we know from home. There are no polished stones, no neatly folded sheets of ice, no bubbling liquids sloshing around. Instead, space is filled with something far more elusive and strange: diffuse clouds of gas, electric seas of plasma, and ancient motes of cosmic dust. Cold, dark, and quietly waiting. These are the raw materials of galaxies, the very bones of the cosmos, yet they exist in states that defy our earthbound instincts. Out there, matter doesn't play by familiar rules. Let's begin with the interstellar medium, or ISM for short. This is the space between stars, not empty, but surprisingly rich in complexity. It's made of gas, dust, plasma, and magnetic fields, all drifting through the arms of galaxies. It might look like a vacuum, but zoom in close enough and you'll find a dynamic environment, a kind of galactic weather system filled with turbulence, temperature fluctuations, and mysterious radiation. It's a place where matter is stretched thin, so thin that in a volume the size of your living room, you might find only a few atoms, and yet these scattered atoms add up. Over vast distances they form clouds, filaments, and structures that cradle star formation. and influence entire galactic ecosystems. Most of the matter in the interstellar medium is hydrogen, the simplest and most abundant element in the universe. Sometimes it floats as individual atoms, known as neutral hydrogen, and sometimes it pairs up into hydrogen molecules. But much of it doesn't stay neutral for long. Ultraviolet radiation from stars or energetic collisions can strip electrons from these atoms, turning them into ionized gas. And once that happens, we enter the realm of plasma. Plasma is often called the fourth state of matter, and in space it's not just common, it's dominant. Stars are massive balls of plasma. Solar winds are rivers of plasma. Nebulae glow with the energy of ionized gases. These plasmas behave differently from ordinary gases because their charged particles interact with electromagnetic fields, creating structures and behaviors that are both intricate and unpredictable. Instead of drifting gently, they swirl, loop, and erupt. They form waves, filaments, and magnetic bubbles. If gases are the clouds of the universe, plasma is the lightning within them. Yet not everything in space is hot. Far from it. In the vast, lightless gaps between stars, temperatures can drop to just a few degrees above absolute zero, and there, floating in these frozen stretches, is dust. Not the fluffy kind that collects on shelves, but microscopic grains made of carbon, silicates, ice, and metal compounds. These dust particles may be tiny, often no larger than a smoke particle, but they are essential to the story of matter in space. They absorb and scatter starlight, helping to shape the glow of distant galaxies. They act as surfaces where molecules can form, including the crucial ingredients for life, and in the dark cradles of molecular clouds, they help cool the surrounding gas, allowing it to collapse into new stars. These molecular clouds are among the most fascinating structures in the universe. Massive, cold, and dark, they are the nurseries of stars. Despite their name, they aren't clouds in the earthly sense. They're vast regions of space, sometimes hundreds of light years across, filled with hydrogen, helium dust, and traces of more complex molecules like ammonia, water, and carbon monoxide. Temperatures inside these clouds can fall to 10 degrees Kelvin or even lower. At such low temperatures, atoms move sluggishly, allowing gravity to slowly pull the material together. Over millions of years, dense clumps form, heating up as they collapse. Eventually fusion ignites, and a new star is born. Hot, bright, and ready to begin shaping its surroundings. The transitions between these phases, neutral gas to ionized plasma, cold dust to star-forming clumps, are not clean, discrete events. They're gradual, often overlapping, and influenced by a wide array of cosmic forces. A single region of space might contain coal dust, warm gas, and pockets of plasma, all interacting in subtle ways. Light from nearby stars can photoionize gas, carving glowing edges into dark clouds. Shock waves from supernovae can compress gas, triggering star formation in one region while dispersing material in another. Gravity, radiation, magnetism, and motion all play a role in shaping these invisible worlds. One of the most unusual features of space matter is its relationship with temperature. On Earth, we think of temperature as something tied to touch. Cold to the skin, hot to the tongue. In space, those cues break down. A cloud of plasma might be millions of degrees hot, but so diffuse that it wouldn't feel warm at all. That's because temperature in physics is a measure of the average energy of particles, not the sensation it gives. In space, where density is extremely low, you can have high temperatures and low heat content at the same time. It's possible to be surrounded by million-degree plasma and still freeze to death. On the other end of the spectrum, there are objects like Bok globules, small, dense pockets of gas and dust that appear as dark blotches against the glow of nebulae. These globules are often sites of early star formation, shielded from radiation and insulated by layers of dust. Inside them, the temperature can be just a few Kelvin, making them some of the coldest natural places in the universe. Matter here is sluggish, quiet, and ready to transform. Even more exotic are the so-called interstellar ices. On the surfaces of dust grains deep inside molecular clouds, atoms and molecules condense and freeze into thin layers. These include water ice, but also methane, ammonia, formaldehyde, and other organic molecules. Under ultraviolet radiation, these ices can undergo complex chemistry, creating more elaborate organic compounds, some of which may be precursors to life. When stars eventually form and heat their surroundings, these ices evaporate and release their chemical bounty into space, seeding the environment for future planetary systems. Beyond our galaxy, the intergalactic medium stretches between clusters of galaxies. It's even more rarefied than the interstellar medium, but contains a vast amount of the universe's baryonic matter. Those ordinary atoms that make up stars, planets, and people. This medium is largely plasma, heated to millions of degrees by cosmic shock waves and galactic activity. It's visible mainly through its effect on light from distant quasars and its signature in the X-ray and radio wavelengths. Even in the emptiest places, matter persists, shaped by gravity and time. Cosmic rays also contribute to the strange behavior of matter in space. These are high-energy particles, mostly protons and atomic nuclei, that travel at nearly the speed of light. They come from supernovae, black holes, and other extreme sources. When they collide with atoms in the interstellar medium, they can break molecules apart, trigger reactions, and alter the chemistry of entire regions. They are tiny messengers of violence and change, adding an invisible spice to the calm appearance of space. All of these components, plasma, dust, gas, ice, and radiation, exist in a constant state of flux. They aren't bound to one phase or another. They transform under pressure, light, and motion, constantly reshaping themselves as they orbit stars, drift through galaxies, or fall into the gravity wells of black holes. In space, the phases of matter are more fluid, more ambiguous, and more responsive than the familiar solid liquid gas trinity we use on Earth. It's a reminder that matter doesn't have to be tidy to be fascinating. Out in the cosmos, it dances to a slower rhythm, shaped by forces spread over light years and lifetimes. It coils in magnetic spirals, rests in shadowed clouds, or blazes in million-degree jets. It builds stars, carves nebulae, and records the history of the universe in its silent rearrangements. Matter in space is not just exotic, it is deeply poetic. It whispers of old stars and future suns. It drifts in slow, grand patterns we're only beginning to see. And though it's far from solid ground, it may be the most essential matter of all, the raw story of the universe, told in the quietest, coldest corners of the sky. We like to think we've got a good handle on the phases of matter. Solids, liquids, gases, plasma. Maybe throw in a few more for flair, like Bose-Einstein condensates or superfluids. It makes for a satisfying list. But nature rarely sticks to tidy inventories. The more closely we look, especially at the edges of known physics, the more it seems likely that we're missing pieces. There may be entire families of phases we've never seen, never touched, never even imagined, hidden in the extreme corners of the universe or waiting in the fine print of quantum mechanics. Let's begin with a curious character from the world of two-dimensional physics, anyons. While everyday matter is made from fermions and bosons, two well-behaved species of particles with clearly defined rules, anyons are the eccentric cousins that show up only in flatland. In two-dimensional systems, the rules of quantum statistics relax just enough to allow a third category. Anyons can have fractional spin and obey what's called fractional statistics. When you swap two anyons, their quantum wave function doesn't just stay the same or flip sign. It can pick up an arbitrary phase factor. It's like having a particle that keeps track of how it's been moved, adding a twist with every swap. That kind of memory makes anyons fascinating candidates for quantum computing, especially for topological qubits that are naturally resistant to noise. Anyons don't exist in everyday materials, but in certain exotic systems, like the fractional quantum Hall effect, they may be lurking. These are engineered environments where electrons behave strangely due to strong magnetic fields and low temperatures. In those settings, the electron fluid can organize itself into a state where excitations behave like particles, with 1/3 the charge of an electron. Are these real particles? Not in the traditional sense, they're quasi-particles, emergent behaviours that arise from collective motion. But just because they're made of interactions doesn't make them less real. If anything, it hints at just how flexible nature is when it comes to defining what matter can be. Now let's take a step deeper into the abyss, into something even more hypothetical: strange matter. This idea comes from the world of particle physics, where it's been suggested that under extreme conditions, matter composed of up and down quarks, the kind that make up protons and neutrons, could transform into something denser, something made of up, down, and strange quarks. This substance is called strange matter, and it could be more stable than regular atomic nuclei under the right conditions. It's possible that in the cores of neutron stars where densities crush matter into unimaginable compactness, strange matter might naturally form. If so, these stars could become strange stars, celestial objects made almost entirely of a new phase of quark-rich matter. And here's where it gets even stranger. If strange matter is truly more stable, then a chunk of it drifting through space could hypothetically convert normal matter into more strange matter upon contact. It's a bit of a doomsday thought experiment, one stable droplet turning everything it touches into itself. But don't worry, there's no evidence that's happening anytime soon. Still, the concept suggests that matter might have deeper levels of stability we haven't yet accessed. Strangelets are the theoretical chunks of this stuff. Tiny, stable bits of strange matter that could, in principle, exist on their own. If we could isolate and study them, they might open a window into the strong force and the behaviour of quarks under ultra-dense conditions. But so far they remain elusive, more idea than object, more ghost than guest. And while we're down in the core of dense stars, we might as well mention the idea of quark stars. These are theoretical objects that could form when neutron stars are compressed beyond their usual limits. Instead of neutrons, the matter inside becomes a sea of unbound quarks. Not quite a black hole, but not a neutron star either. Just an incredibly dense, stable ball of quark matter. It's a phase transition on a cosmic scale. Ordinary matter crushed into a fluid of its most fundamental components. We don't know for sure if quark stars exist, but they are a serious possibility. Observations of unusually small, dense neutron stars, or sudden shifts in the brightness of pulsars, might one day provide the clues we need. If confirmed, quark stars would represent a phase of matter far beyond anything we can create on Earth. It would mean that entire objects in the universe exist in a state we've only speculated about in equations. Now, let's go even more speculative. What if there are phases of matter that don't even involve the kinds of particles we know about? What if dark matter, this invisible substance that makes up roughly 85% of the universe's matter, has its own phases, its own transitions, its own forms of complexity? We don't know what dark matter is. It doesn't interact with light, so we can't see it directly. But we know it's there because of its gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the cosmos. It acts like matter, but refuses to be caught. Some theories suggest it might be made of weakly interacting massive particles, or WIMPs. Others suggest axions, tiny light particles that barely interact with anything. But what if dark matter isn't just a sea of isolated particles? What if it forms bound states, structures, even new kinds of materials? There are ideas floating around about dark atoms, composed of dark protons and dark electrons, interacting through a kind of dark electromagnetism. If that's the case, then dark matter might form dark molecules, dark liquids, even dark crystals. These would be phases of matter that exist in a parallel world, hidden from us by the lack of interaction with ordinary light and matter. In that case, the universe could be filled with unknown complexity running alongside our own, but completely invisible to our senses. If such phases exist, how would we find them? Perhaps through subtle gravitational lensing, or tiny discrepancies in the cosmic microwave background. Perhaps in underground detectors, waiting for the faintest ping of a dark particle brushing past. Or perhaps we've already seen the signs, but haven't recognized them for what they are. Even within ordinary matter, we may still be missing phases. In the lab, we've created supersolids, time crystals, and topological insulators, all of which were theoretical before they were real. Each time we push the boundaries, cool something further, squeeze it tighter, or isolate it more precisely, new behavior emerges. Matter is a master of reinvention. One of the key reasons we keep finding new phases is because matter isn't just made of particles, it's made of relationships. The way particles interact, align, entangle, and self-organize creates new emergent properties. It's not just about the ingredients, it's about the recipe, the temperature, the pressure, the timing, and the symmetries, or lack thereof. A new phase isn't necessarily about discovering a new substance. It's about finding a new way for particles to cooperate. Quantum computers, for example, are pushing us into regimes where entirely new kinds of matter might appear. Systems cooled to near absolute zero and manipulated with laser precision could reveal behaviors we've never seen. And who's to say what lies beyond those boundaries? Maybe there are quantum liquids or entangled lattices still waiting to be discovered. The history of physics is in many ways a history of being surprised by matter. Every time we think we've catalogued it all, nature offers us a twist, something unexpected, elegant, and often a little weird. It's a gentle reminder that our categories are just snapshots, taken from the limited perspective of where and when we happen to live. There may be phases of matter that exist only inside black holes, or at the hearts of galaxies, or in the first picoseconds after the Big Bang. There may be forms of matter that require an entirely new kind of physics to describe, beyond the standard model, beyond our current understanding of quantum mechanics. And some of those may be unimaginably beautiful. So, are we missing phases of matter? Almost certainly. Are they strange? Without a doubt. But they are also clues, trails of cosmic breadcrumbs leading us toward a deeper understanding of how the universe arranges itself, how complexity emerges, and how even the quietest particles can surprise us when they gather in just the right way. At the heart of quantum physics lies a quiet little mystery that refuses to sit still. It's not just that particles behave like waves, or that they can exist in superpositions. It's that the very act of observing them, of checking in on what they're doing, can change what they are. In this strange landscape, the line between what exists and what is measured becomes more of a gentle blur than a solid boundary. And when it comes to the states of matter, this leads us somewhere especially peculiar. A phase might not always be something absolute. Sometimes it might be shaped by context, by environment, even by observation itself. In the classical world, the world of ice cubes and iron bars, we tend to think of phases as straightforward and permanent. A solid is a solid. A gas is a gas. These identities are grounded in measurable properties like structure, compressibility, and temperature. But in the quantum world, things are more flexible. Particles are more like probabilities smeared out across space until they're pinned down by a measurement. States exist not as rigid configurations, but as evolving clouds of potential. Now imagine trying to define the phase of matter under those conditions. What does it mean to say something is in a phase if it hasn't yet resolved itself into a definite state? Can matter have a phase before anyone looks? Or does the phase emerge through interaction with its surroundings, or even with the experimenter? Let's take quantum phase transitions as a starting point. Unlike classical phase transitions, which are driven by thermal energy, melting, boiling, freezing, quantum phase transitions happen at absolute zero, driven not by temperature but by fluctuations in quantum fields. These transitions depend on parameters like magnetic field strength or particle interactions, and they involve entire systems reorganizing their ground state, the lowest energy configuration. This is not about jiggling particles with heat. It's about shifting the underlying rules. In these systems, the definition of a phase isn't just about where the atoms are, but about how they're collectively behaving at the quantum level. Are the particles entangled in a certain way? Are they following a particular symmetry? Is there a topological twist to the way their wave functions are arranged? These are subtle, almost philosophical questions, and they only become meaningful when we define the framework we're looking through. In fact, some quantum phases can only be distinguished by the way they respond to certain kinds of measurements. Two systems might look identical in terms of particle distribution or energy levels, but behave differently when you twist them or probe their edges, or trace how their quantum states braid around each other. The identity of the phase is encoded in how the system interacts with us, and with the tools we use to explore it. This leads to an even deeper idea. That phase is not always a fixed property of a system, but something emergent, dependent on what we're measuring, when we're measuring it, and even from what angle. In condensed matter physics, there are examples of so-called symmetry-protected topological phases, states that remain distinct only as long as certain symmetries are preserved. Break the symmetry, and the distinction between phases disappears. The phase is real, yes, but it's also delicate, conditional, like a snowflake that holds its shape only under the right kind of light. Then there's the quantum Zeno effect, a charming oddity where the mere act of observation can freeze a system's evolution. In a very real sense, watching a quantum system too closely can prevent it from changing. It's like trying to let a souffle rise while constantly opening the oven door. The measurement resets the system, pinning it back into place. Could that influence its phase? In highly controlled systems, possibly yes. When the act of observing affects the energy landscape, the boundaries between phases begin to wobble. Now consider quantum entanglement, a phenomenon where two or more particles share a state, such that measuring one instantly affects the other, no matter the distance between them. In systems with many entangled particles, the structure of that entanglement itself can define the phase. Not the particle positions, not the temperature, but the invisible mathematical web that links their quantum states. It's a phase of relationships, not things. It's like describing the mood of a room based on eye contact alone. In these cases, a phase is something almost abstract. It doesn't always manifest as a tangible feature like rigidity or flow. It's encoded in the system's correlations, in the shapes of its quantum fluctuations, and in the responses it gives when nudged by just the right probe. You can't always see the phase. You have to ask the right question. And sometimes, if you ask a different question, you'll get a different answer. This idea touches on the deeper philosophical debates around quantum mechanics. What is a state, really? Is it something that exists independently, waiting to be discovered? Or is it something that coalesces out of the fog when measured? Different interpretations of quantum mechanics offer different answers. The Copenhagen interpretation suggests that quantum systems don't have definite properties until measured. The many worlds interpretation says they do, in all possible versions of reality at once, and pilot wave theories offer an elegant undercurrent of determinism beneath the surface. But no matter which interpretation you prefer, they all agree on one thing. The act of observation cannot be ignored. Measurement is not just a passive glance. It's an interaction that shapes the system. In some cases, it defines it. This principle has profound implications for the nature of phases. If observation is part of the system, then phases become contextual. What we see depends on how we look. It's not that reality is slippery exactly, it's that it's participatory. The observer is part of the dance. There are experimental hints of this in systems like quantum simulators and cold atom traps. In these setups, researchers can build artificial quantum materials with tunable interactions and geometries. By changing the way they measure the system, using different types of probes, or entangling certain parts, they can induce phase-like behavior that only exists under those conditions. It's not trickery. It's not illusion. It's physics at the edge of philosophy. In this framework, the boundaries between phase, state, and system begin to dissolve. Matter becomes less of a thing and more of a behaviour, a performance shaped by context. And our role in that context isn't just to watch, it's to participate. This is not to say that everything is relative or that nothing is real. Phases still obey rules. They still have measurable consequences. Superfluids still climb walls. Time crystals still oscillate. But underneath the surface lies a softer truth. That matter is more flexible than we thought. It can be both stable and uncertain, both concrete and conditional. In a way, this mirrors our own experience of the world. Emotions, identities, and relationships often depend on context, on the moment, the interaction, the perspective. Perhaps matter, at its most fundamental level, shares that same kind of subtlety. So when we talk about the phases of matter, we're not just talking about categories in a textbook. We're talking about the evolving language of structure, interaction, and perception. A quiet interplay between what is, what could be, and what we choose to see. And that's what makes quantum physics feel almost poetic. Not because it's vague, but because it's layered. It allows for certainty and mystery to coexist. It shows us a universe where even the states of matter, those most basic building blocks, are not entirely immune to the gentle nudge of a curious mind. Matter is not just substance, it is story, and the storyteller, it turns out, is sometimes us. Change is the quiet current that runs beneath everything. From the boiling of tea to the slow rusting of iron, from a snowflake melting on your glove to stars collapsing in distant galaxies. Transformation is not the exception, it's the rule. We live in a world defined by transitions, not just the sweeping dramatic ones, but the tiny ones too, the ones you don't notice until they've already happened. Matter, for all its seeming permanence, is constantly rearranging itself, sometimes boldly, sometimes softly, but always in motion. Let's start with a comforting classic, the transition from solid to liquid. We've all watched ice melt, seen butter soften in a pan, or felt a chocolate bar betray us on a summer's day. But behind these familiar moments is a molecular rebellion. In a solid, atoms are arranged in a fixed pattern, vibrating in place like dancers in a tightly choreographed routine. Add heat, and the vibrations grow, they jitter, they push boundaries. Eventually the energy becomes too much for the structure to hold, and the orderly pattern breaks down. The dancers let go of their partners, and the solid becomes a liquid. Liquids are freer, but not completely lawless. The particles slide past one another, still close but no longer tethered to fixed positions. They can flow, take the shape of their container, swirl and shift. And as heat continues to build, these liquid particles gain even more energy, enough to break free entirely and become a gas. Boiling is a spectacular moment of transformation. It's not just bubbling water, it's the birth of chaos at a molecular level. Particles go from colliding with each other constantly to racing through open space, bouncing off walls, and occasionally off your face when the kettle steams. This is matter liberated. The same atoms, now with the freedom to occupy far more space, moving with speeds that depend only on temperature and the occasional bad pun about entropy. But transitions don't only move in one direction. Cool the gas, and condensation takes over. Particles lose energy, slow down, and start to stick. Clouds form. Fog rolls in. A bathroom mirror fogs after a hot shower, not from some mysterious force, but because gas molecules have slowed just enough to settle into the liquid phase again. They're not disappearing, they're just shifting roles. One moment, vapour. The next, a drop. These everyday transformations, melting, boiling, freezing, condensing, are all phase transitions. They mark boundaries between states of matter, but those boundaries are more like riverbanks than brick walls, and if you linger at the edge, you'll find places where both states exist at once. Consider the triple point of water, the precise combination of temperature and pressure where solid, liquid, and gas phases coexist in perfect balance. It's a kind of molecular negotiation, a rare peace treaty in the world of matter. At that point, ice melts and boils, water freezes and evaporates all at once. It's an exquisite reminder that nature is capable of profound balance, even among conflicting behaviours. Or take sublimation, where solids skip the liquid phase entirely and turn straight into gas. Dry ice does this theatrically, turning solid carbon dioxide into a billowing cloud. But regular ice can do it too, just more slowly. That's why freezer-burned food looks shriveled. The ice inside has sublimated into gas over time. Even snow on a sunny cold day might vanish without ever becoming slush. It's not a trick, it's just another path on the map of transitions. Then there's deposition, the reverse of sublimation, when gas becomes a solid without ever being a liquid. Frost on a window pane is an artist's signature in deposition. Water vapour, drifting through the air, encounters cold glass and settles directly into icy patterns. No puddle, no dripping, just delicate crystals, skipping the liquid middleman entirely. All of these processes are part of the natural life of matter, but what makes them especially interesting is that even the most rigid, seemingly immutable substances are not immune to change. Solids don't just sit there waiting, they shift too, albeit more slowly. Rocks, for instance, might seem like the very picture of permanence, but under pressure, over millions of years, they flow. The Earth's mantle, made of solid rock, moves in slow currents, like cold molasses. Glaciers, towering rivers of ice, slide down valleys under their own immense weight. They creak and groan, changing shape with each passing year. Even metal beams in buildings expand in the summer heat and contract in the winter cold. Steel breathes, if you're patient enough to watch. Phase transitions aren't just mechanical, they're deeply emotional too. There's something universally resonant about transformation. Watching wax melt, or chocolate harden, or clouds gather and dissipate can feel almost symbolic. Matter reminds us that change is not something to fear. It's built into the very structure of reality. And sometimes, these transitions aren't even about temperature. Pressure, magnetism, and even light can drive changes in state. Carbon, under extreme pressure, becomes diamond. Certain materials change from insulators to conductors with a flick of voltage. Some switch behaviors when exposed to ultraviolet light. Phase transitions are everywhere, and they don't always announce themselves with steam or sparkle. Sometimes they whisper, changing the rules without changing the shape. One subtle transition is glass softening over time, not the myth of cathedral windows flowing like syrup, but a more precise reality. Even solid-looking materials can relax their internal stresses, reshape their structure, or slowly deform. Crystals can shift alignment. Plastics can harden or crack, and biological materials, like proteins or cells, can transition between active and dormant states depending on their environment. The line between phase and function gets blurry, but that's part of the beauty. In living systems, phase transitions play essential roles. The membranes of cells switch between rigid and fluid depending on temperature and lipid composition. Proteins fold into specific shapes, sometimes snapping into new forms like miniature phase changes. Even the brain operates with transitions, from sleep to wakefulness, or from calm to focused. These aren't phases in the physical sense, but they share the same structure. Different states, triggered by thresholds, capable of sudden or gradual shifts. If you've ever sat by a lake and watched the mist rise, you've seen phase transitions in slow motion. Water warmed by sunlight evaporates into invisible vapour, which drifts into the cooler air above and condenses again as it meets dew point. The whole process cycles over and over, no boundaries, no urgency. Just the universe shifting gears, as it always has. Even our breath is part of this dance. We exhale warm, moist air. In the cold, it condenses into fog. On a warm day, it disperses silently. You're a walking, talking engine of phase transitions, body heat warming the air, cells balancing electrolytes, your skin radiating energy into the night. And at the heart of it all is this simple truth: matter does not stay still. It reshapes itself with every nudge of energy, sometimes gradually, like metal slowly oxidizing, sometimes violently, like lava erupting from a volcano, but always, always in motion. Phase transitions are not the edge of stillness. They are the very signature of life in a physical world. There's a quiet comfort in knowing that even the most solid things are changing. Nothing is static. Nothing is stuck. Not ice, not stone, not even stars. And if everything around you is shape-shifting, if even atoms can reinvent themselves, then perhaps there's something freeing in that for us too. Matter doesn't fear transformation. It leans into it. It stretches, melts, reorders, crystallizes, and moves forward without regret. It's a process that's never finished and never rushed, just like us. In the stillness of night, when the world softens and slows, it's easy to imagine that things are holding still, that the lamp on your bedside table is just sitting there, that your blanket is resting quietly, and that the air around you is unchanged from moment to moment. But as we've drifted through the strange and shifting world of matter, one thing has become clear: stillness is only an illusion. Everything is always becoming. Solids may look steady, but their atoms hum with energy. Liquids seem calm, yet their molecules are constantly reshuffling. Gases are in a never-ending dance, flowing, expanding, fading into the dark. And beyond these, we've found phases that challenge the very definitions we've held on to. States that move without friction, crystals that pulse in time, plasmas that shimmer through the stars, and quantum landscapes where matter remembers, forgets, and reforms. We once thought matter could be divided neatly into 3 categories, but like most things in nature, the truth is more nuanced, more intricate, and more beautifully messy than we expected. It turns out that matter doesn't just exist. It responds, transforms, reacts, and evolves. It flows not just across space, but through possibility. What it is can depend on its temperature, its pressure, its quantum entanglement, and sometimes even the fact that we've looked at it. This isn't a failure of science, it's its greatest strength. The fact that we keep discovering new states, new behaviors, new transitions is not a sign of confusion. It's a sign that we are still listening, still learning, still watching as the universe quietly reveals its layers. Even the names we give to these states, superfluid, time crystal, stringale, feel like poetry. They remind us that science is not just about precision and order. It's about curiosity, about asking, what else? And then leaning in when the answer is stranger than we expected. And just maybe, all of this reminds us something about ourselves, that we too are not fixed, that just like matter, we are shaped by our environment, by our relationships, by what we absorb and what we release. We can be structured, chaotic, fluid, or somewhere in between. We change with time and with experience. We undergo transitions, some subtle, some seismic, and those transitions aren't something to be feared. They're how we grow, how we expand, how we become. So as you settle deeper into rest tonight, surrounded by things that seem still, take comfort in knowing that the world around you is alive with quiet motion, that even in silence, molecules shift, that even in darkness, matter dreams. And if you've made it this far and your eyes are still open, well, perhaps this video was a little too interesting. But I hope it made you smile. If you're feeling generous,